Hey guys, my name is Deb Sarine. This is the assignment 2, part 1 for PIDP 3240. A little bit about myself. I have been instructing the electrical trade for 6 years now. So as subject matter experts on electricity, we got hired straight out of the field. And then SAIT required us to learn more about the teaching aspect of our job, which is good. Obviously, we should do that. So that's why I'm taking PIDP. This is my last course before my capstone, so almost finished. Yeah, so just a couple of housekeeping things. We're going to use Zoom and its little reactions. So if you guys have a question for something that I'm talking about, go ahead and, use a reaction, like put your hand up or thumbs up or whatever, I'll see it. Or you can type it into the chat. However, I think I probably won't see that as easy as a little hand popping up on your screen. So yeah, go ahead, feel free and stop me, ask any questions throughout. And yeah, I think that's it, all we have to cover. So we're gonna get started here. Can you guys see my screen? Everything on it? Yeah, okay. Okay, so today I'm gonna be talking to you guys about adding resistors in parallel. Okay, so you might be asking yourself why it's important to know how to add resistors in parallel. So electrons give off energy in the form of heat. So it's really important for electricians to know how to properly size conductors and overcurrent protection so that they can properly manage and contain that heat and prevent any sort of damage such as a fire caused by that heat, okay? Okay, so on a scale of 1 to 5, how much do you know about electricity? 1, okay.
Sorry, just trying to.
2?
2 or 3.
Okay, awesome.
I'll go with 2 or 3 as well.
Okay.
Maybe 2.
So that's great. That means that there's some room and some opportunity for some learning and some growth here in your understanding of electricity. So awesome. Okay, so this is a very basic circuit. There's just one load, so one path for current to flow. In the middle is the electrician's holy grail of formulas. This is Ohm's law. Ohm's law basically talks to us about the relationship between current, voltage, and resistance. And when current goes up, resistance has to go down because they have an inverse relationship. Does everybody understand what an inverse relationship is? Kind of, sort of. Okay. So basically, you can think about it like the furnace in your house. As the temperature goes down, it kicks on and calls for current. So now current has to go up because the temperature is going down. So like an inverse relationship. And then if we take a look at voltage and current, when voltage goes up, current will also go up because they have a direct relationship. So basically, it's really just the position that they're in around the equal sign, right? So current is in the numerator position and resistance is in the denominator, so opposite positions. Any questions on that? All right. Oh, someone's trying to join. Is that a thing? What? Sure. Okay, so if we take a look at a circuit now that has 3 loads on it, okay, you guys will notice that current comes to a junction point where it needs to split. It needs to feed the load that it's reached as well as carry on down the line to feed additional loads connected to that circuit. At the end of its job, current then has to combine together and collect to return back to the source. Okay. All right, so if we take a look at what's going on with voltage, basically I have taken a wire to extend one side of the source to the, sorry, one side of the source to the other side, one side of one of the resistors or a load. So basically anything that consumes current. In this example, we're just using basic resistors. And then I continue on with another wire to extend to one side of another load and do that again for the third. I'll also take a wire from the other side of the source and connect it to the other side of all three of the loads. So basically, we could say that all of the loads then are connected to source voltage. So all loads in parallel have the same voltage. Does that make sense? All right, cool. Man, now we're really popular here, guys. Okay. So now let's take a look at what's going on with current. I like to use an analogy here to make it a little bit more simple. So we're going to use the analogy of prisoners and prison work camps. Okay, so the prison bus is leaving the prison first thing in the morning. And depending on how many work camps I have, that's going to determine how many prisoners I have to leave the prison in the morning, right? So I've got a rock breaking work camp. I've got a litter pickup work camp, and I've got a gardening work camp. So I need enough prisoners to leave the prison in the morning to fill all of those work camps. Now, if we consider prisoners like current, the more work camps I have, the more prisoners I would need, correct? Therefore, I'm requiring more current from the source. Cool. Okay, so back to our favorite formula ever in electricity. We've determined that the voltage is going to stay the same in a parallel circuit across all the loads. We know that current is going to be going up in a parallel circuit. So because of the inverse relationship with resistance, we know that resistance must be going down, right? All right. So now let's take a look at how we do that. So I had messaged in Twitter about having a scientific calculator. If you don't have one, that's fine because I have the pictures here on the slides. But basically, we need an EL546X or a sharp EL520X, really any kind of a sharp. And that's because when you as the students go write your trade qualification exam, this is the calculator that they provide for you. So instead of trying to have to learn a new calculator like during your final exam, we just work with that calculator throughout the course so that you're quite familiar with it. So we want to pay attention to the second function button as well as the number 2 button. And you'll notice the X to the -1 above the number 2 button. That's going to be the 1 over button that we need to use in order to add resistance in a parallel circuit. Okay, so this is the formula to add resistance in a parallel circuit. We can't add them directly because that would result in a higher number. And we know that the current and voltage have, or current and resistance have an inverse relationship. We know current's going up, so resistance has to go down. So we are, what is happening?
I don't know who this person is. Yeah, there you go.
Okay. Well, this will make for an interesting video to post. Okay. Holy moly. So, basically, I'm going to transpose this formula. So this is the one that you're going to see in your individual learning module package, but we're going to transpose it to the one popping up on your screen right now because now I have technical difficulties because she drew on it. Oh, good gravy, guys. Okay.
Could you go to your previous slide and then try again?
Oh, she drew like on the screen. How do you get rid of that?
I don't know. That's really unfortunate.
It is very
Whoever that person was.
Huh. Okay.
Do you have the option of clearing, just really quickly, do you have an option of clearing any, like,
Okay. So transposing that formula using the 1/over button in our calculator, basically we've just taken that formula above, transposed it to the one that you see on the screen right now, so that it'll be easier when we punch it into our calculator. All right, so let's take a look at how we do that. So we're going to use that same circuit that has 3 loads. The first resistor is going to be worth 13 ohms of resistance. The next one's 25 ohms of resistance. And finally, we'll have 10 ohms of resistance. Okay, so that'll be our circuit. So now we're going to take a look at punching it into our calculator. Oop, back up a slide. All right, so with our calculator, we just want to hit this 17 for 17. And then make sure you hit the second function button and then the number 2 button. And you'll see on the display that you'll get 17 to the -1. So that's representing the 1/17 for us. Then you can go ahead and press the plus button. Step 2, we're just going to follow the same sequence. We're going to hit 25 and then the second function button and then the number 2 button to get 25 to the -1 and add the plus button in, so that we can add our last load of 10 ohms by pressing 10 and then second function button and then the 1/over button. Okay. Go ahead and hit the equals button and you'll notice that the number that you get is a really small number. It's always going to be less than 1. And there's one final step that we have to complete in order to finish our resistance total calculation. We have to 1/over the whole answer. So that's a good indication when you're calculating out resistance total in parallel. If you end up with a really small number like that, you need one more step in order to get resistance total. So basically we just want to do the same thing. We want to hit the second function button and then the number 2 button, and up in the screen it'll say answer 1/over. Go ahead and hit the equal sign and you'll notice that the overall resistance for this circuit is 5.03 ohms. One thing to pay attention is that the resistance total is lower than any of the resistors in the circuit, right? And that's because with Ohm's law and that inverse relationship, we know that if current's going up, resistance has to be going down. So another little trick when you're calculating, if you ever end up with a resistance total number that's bigger than any of your resistors, then you better go back and do that calculation again. Okay, any questions with that? All right. So resistance total will always be lower than the smallest resistor. And that's because of the inverse relationship that we know resistance and current have according to Ohm's law. So again, if we go back to our original analogy with the prisoners in the work camps, we know that the more prison work camps we have, the more prisoners we need to come from the prison in the morning, i.e. more current, okay? And at the end of the day, all the prisoners need to be going back to the prison, or else we're going to send the dogs out to search for them, right? Or in other words, all the current needs to return back to the source. Otherwise, there's something wrong with your circuit, okay? So things to remember in a parallel circuit, we know that voltage is always going to stay the same in a parallel circuit. We know that current is going to go up as we add loads in a parallel circuit, which means resistance has to be going down. And we know that resistance total will always be less than the smallest resistor in the circuit. Okay. Does anybody have any questions about that? No, eh? Wow. All right, perfect. Well, now on a scale of 1 to 5, how do you feel about your electrical knowledge?
Feel I'm up to about a 4 now.
Nice.
I still think
ready.
I don't think I'd remember all of this, but I think I'd have
Yes,
a
I agree.
basic understanding.
Awesome.
I'm at a 2.5 now. 2.5.
Okay,
I feel like
perfect.
I learned more. Yes.
So there was learning and growth.
Yes, absolutely.
Wonderful. All right. Well, thank you guys for coming to my presentation.